The idea of replacing hydrogen with hydrogen peroxide as a fuel might sound like a curious twist. After all, hydrogen fuel cells already seem futuristic. They split hydrogen at one electrode, combine it with oxygen at the other, and yield nothing but water as waste. Why meddle with something so clean? And yet, hydrogen itself is notoriously difficult to handle. It is the smallest molecule in existence, leaks easily through metals, requires high-pressure storage or cryogenics, and needs costly infrastructure. By contrast, hydrogen peroxide, H₂O₂, is a liquid at room temperature, can be transported like gasoline or ethanol, and already has a century of industrial production behind it. Could it be that the future of clean energy lies not in the most obvious fuel, but in its more manageable chemical cousin? From a scientific perspective, hydrogen peroxide is fascinating because it can play the role of both oxidizer and fuel. In a peroxide-based fuel cell, H₂O₂ can be reduced to water at one electrode while being oxidized to oxygen at the other, producing electricity in the process. Unlike hydrogen gas, which requires a separate oxygen supply, peroxide already contains both elements in one molecule. Theoretically, this simplifies system design and raises energy density. And because H₂O₂ is a liquid, it avoids the engineering nightmares of storing compressed hydrogen tanks. Doesn't this suggest that some of hydrogen's biggest weaknesses might be sidestepped by choosing a different carrier altogether? Engineers, however, confront a thornier reality. Pure H₂O₂ is highly unstable, decomposing explosively in the presence of metals or heat. Stabilized solutions are safer but carry lower energy content per kilogram than hydrogen gas. Catalysts are also critical. Many materials corrode or degrade under peroxide conditions, so electrodes need to be designed from exotic, resilient compounds. Another limitation is production. Industrial peroxide today is made using anthraquinone chemistry, an energy-intensive process not yet optimized for green scalability. Could it be that the real question is not whether peroxide works in a lab, but whether we can make, store, and use it sustainably at scale? A lesser-known fact is that peroxide fuel cells are already being tested in niches where their liquid form is an advantage. Submarines and underwater drones have used peroxide-derived fuels because they don't require external oxygen. Some prototypes of direct H₂O₂ fuel cells operate at relatively low temperatures and deliver impressive power densities in lab tests. Research even shows that enzyme-inspired catalysts like peroxidases or amino-based complexes might provide cheap, stable alternatives to platinum. These developments hint that peroxide systems could carve out applications where hydrogen struggles: compact, safe storage for remote or underwater power, or portable generators that don't need high-pressure tanks. The paradox, then, is that hydrogen peroxide fuel cells look both more practical and more problematic. Easier to store, transport, and integrate into existing infrastructure, yet plagued by instability, corrosivity, and limited green production routes. If solutions emerge, stable high-concentration storage, durable catalyst, renewable synthesis methods, peroxide could become a serious rival or complement to hydrogen. The haunting question is whether industry will invest in perfecting this liquid hydrogen alternative or whether peroxide will remain confined to niche applications. If history is a guide, the future of clean energy may not belong to the purest solution, but to the one that balances chemistry, safety, and practicality best. Hydrogen peroxide, H₂O₂, is emerging as an alternative fuel that can directly generate electricity in fuel cells. Unlike hydrogen gas, which requires storage under high pressure or cryogenic conditions, H₂O₂ is a liquid at room temperature, making it easier to handle, store, and transport. In fuel cells, it can act both as an oxidant and as a fuel, depending on design, offering dual flexibility. Researchers envision peroxide-based fuel cells as a cleaner, simpler route to chemical to electrical energy conversion. The paradox begins here. A molecule long seen as a disinfectant could power future cars, drones, and grids. Its duality of being both common and extraordinary raises the question of whether it can surpass hydrogen. Recent studies have demonstrated H₂O₂ fuel cells that produce stable power at room temperature using platinum or non-precious catalysts. It is like discovering that the liquid you use to clean a wound could also drive an electric car. Hydrogen fuel cells face major challenges: storage at 700 bar pressure, boil off at cryogenic temperatures, and safety risks from leaks. Hydrogen peroxide avoids these problems by existing as a stable liquid that can be shipped in tanks like gasoline. Distribution through existing liquid fuel infrastructure could reduce the cost barrier that hampers hydrogen adoption. In addition, H₂O₂ fuel cells can be designed to operate at ambient conditions without complex systems. These advantages suggest a pathway where peroxide-based systems solve hydrogen's logistical bottleneck. Liquid-fueled drones powered by concentrated H₂O₂ cells have already been tested as an alternative to compressed hydrogen. It is like switching from carrying balloons of gas to carrying a bottle of water that does the same job. The energy density of H₂O₂ is lower than pure hydrogen, but its electrochemical conversion can be efficient when catalysts are optimized. The decomposition of H₂O₂ releases oxygen and water, enabling reactions that mirror those in hydrogen fuel cells, but without external oxygen supply. However, side reactions, radical formation, and instability at electrodes can reduce efficiency. Optimizing redox potentials and minimizing parasitic losses is key to making peroxide cells viable. The paradox lies in balancing stability with reactivity. The very property that makes H₂O₂ useful in cleaning also complicates energy harvesting. Laboratory peroxide fuel cells already achieve efficiencies around 50–60%, approaching those of hydrogen cells under certain conditions. It is like trying to harness the fizz from soda for power. You want the release to be steady, not explosive. Hydrogen peroxide fuel cells rely on catalysts that can handle both reduction and decomposition pathways without being destroyed. Platinum works, but cost and durability remain barriers. Non-precious metal catalysts, such as manganese oxides, cobalt oxides, and even single-atom catalysts, are under investigation. A major hurdle is preventing unwanted decomposition of H₂O₂ into water and oxygen, which wastes energy. Achieving selective, stable catalysis is the central research frontier. The paradox is that the simplest molecule requires the most subtle control. Researchers at universities in Japan and China have reported cobalt-based catalysts with high selectivity for H₂O₂ reduction in fuel cells. It is like training a wild horse. You must guide its energy carefully, or it bolts away uselessly. Hydrogen is explosive and prone to leakage, but hydrogen peroxide carries its own safety issues. Concentrated H₂O₂ is a strong oxidizer and can be hazardous if mishandled, decomposing violently under heat or contamination. Safe handling protocols and stabilizers are essential for practical applications. However, compared to compressed hydrogen at hundreds of atmospheres, liquid peroxide may still present a lower overall hazard profile. The trade-off is between explosive invisibility and reactive visibility. Rocket industries have long used concentrated H₂O₂, or high-test peroxide, as propellant, proving it can be handled safely with protocols. It is like choosing between storing invisible fireworks in your garage versus a jug of bleach. Both require care, but one is harder to control. Hydrogen peroxide decomposes into water and oxygen, making its byproducts environmentally benign. Its synthesis, however, is energy-intensive, relying mostly on the anthraquinone process with fossil fuels. For H₂O₂ fuel cells to be truly green, sustainable production methods, or renewable-powered processes, must scale up. If achieved, peroxide could be both fuel and oxidizer in a clean cycle. The paradox is that a green fuel must itself be made green, or it is no better than hydrogen made from coal. Recent research in photocatalytic water oxidation and oxygen reduction is producing H₂O₂ directly from air and water using sunlight. It is like owning an electric car that only counts as clean if the electricity comes from solar panels, not coal plants. Hydrogen peroxide fuel cells may find their first niches in portable and small-scale systems, drones, underwater robots, field sensors, and emergency backup units. Their liquid storage and compact infrastructure make them ideal for remote or hostile environments. Larger-scale applications like cars or grid storage will require breakthroughs in catalyst durability and peroxide production. In such a trajectory, peroxide fuel cells may complement rather than replace hydrogen fuel cells, with both coexisting and each dominating its own domain. Submarines already use hydrogen peroxide as an oxygen source for propulsion, hinting at future military and civilian marine applications. It is like candles and light bulbs, coexisting different technologies for different niches of illumination. Skeptics argue that H₂O₂ fuel cells will remain niche because hydrogen offers higher energy density and already attracts massive infrastructure investment. Peroxide's instability at high concentrations and limited large-scale synthesis are serious obstacles. Proponents counter that hydrogen's infrastructure problems are equally daunting and that peroxide offers a more plug-and-play solution with existing fuel systems. The paradox is that both fuels are green in theory, but struggle in practice, so the winner may depend more on economics than physics. Despite decades of hype, hydrogen cars remain rare. Peroxide may face a similar adoption curve. It is like two runners in a marathon, where both are carrying heavy weights. Victory goes not to the fastest, but to the one who manages the burdens best. The paradox is that hydrogen peroxide fuel cells promise simpler logistics and safer storage than hydrogen, yet their core challenges, catalysis, stability, and green production, mirror the same barriers hydrogen faces. If solved, H₂O₂ could become a liquid fuel standard, merging the convenience of gasoline with the cleanliness of water-based chemistry. If not, it may remain a laboratory curiosity. The future depends on whether peroxide can be produced cheaply and catalyzed efficiently without decomposition. Humanity may be looking at a liquid key to the hydrogen economy, or just another beautiful but impractical idea. A prototype H₂O₂ fuel cell delivering steady power at room temperature with cobalt catalysts shows the vision in miniature. It is like glimpsing a road paved with gold bricks, but only if we can figure out how to manufacture the bricks first.